Hello everyone, in this video we'll be looking at section 13.2, which is limits and continuity, but this time we're looking at functions of several variables, right? Specifically, we'll be looking at functions of two variables. Okay, so just like in functions of single variables, we can look at limits and continuity. That's what we'll be looking at here, but first we need to talk about neighborhoods in the plane. So using the distance formula between 2 points, say x, y, and x sub 0, y sub 0, in the plane, you can define a delta neighborhood about the point x naught, y naught, or x sub 0, y sub 0, with radius delta as this set, right? So this set right here is the set of all points x, y, such that what is this piece right here? This is the distance between x and x naught and y naught. So in other words, so that the distance between the point x naught, y naught and the point x, y is less than delta, right? So what does this delta neighborhood end up looking like? This ends up looking like an open, since it's less than, strictly less than, not less than or equal to, it looks like an open disk centered at x naught, y naught with radius delta. So a delta neighborhood is exactly that. A delta neighborhood centered at x sub 0, y sub 0, x naught, y naught is an open disk centered at that point of radius delta. So for example here, if I'm going to draw my x and y plane, and this is my point, say x naught, y naught, then I would have a nice circle that goes around it to create a disk. And this time when I mean disk, I mean a two-dimensional disk, right? So a circle here. This right here, and if I were coloring this in, is my delta neighborhood. Right? So this is my delta neighborhood. And notice that this distance right here is going to be delta, and that's why it's called a delta neighborhood. So if I take this point right here, x, y, this is a point that lies inside my delta neighborhood because it lies inside the disk. This point out here, xy, is not in my delta neighborhood because it doesn't lie in that disk, right? So when this formula contains a strictly less than, we have an open disk, right? So for instance, this right here is an open disk. If I had, for some reason, less than or equal to, then it would be a closed disk, and I would include the border, so I'd have a solid border around the outside. Let R be a region, or let the region R be a set of points in the plane. So let's go ahead and just draw this region here. So say this is my coordinate plane, x and y, and say this is my region R. Right? And so let me go ahead and color this in here. So this is my region R. It's a set of points in the x and y plane. So a point x naught, y naught is an interior point if there exists a delta neighborhood about that point that lies entirely inside of the region R. So for example here, if I took this point right here, say this is some point, I guess I don't need to label it x naught, y naught, but this point would be considered an interior point. Why? Because I can draw a little disk. This disk is a radius delta, so that the disk is entirely inside of my region R, right? So this right here is an interior point. If every point inside the region is an interior point, then R is an open region. So if the outside of this region, if I had colored this in or dotted instead of colored it in solid, then it would be considered an open region. A point x naught y naught is a boundary point if every open disk centered at that point contains points inside the region and points outside of the region. So for example, if I had this point right here, right, this would be considered a boundary point. Why? Because it contains points that are both, it contains, in the delta neighborhood that contains it, I can find points that are on the outside of the region and points that are on the inside of the region, right? So this right here is a boundary point. If R contains all of its boundary points, then R is a closed region. So for example, the picture I drew here is a closed region. Okay, so now that we have that in mind, let's go ahead and start talking about limits of a function of two variables. And limits of a function of two variables is going to talk about this whole idea of a delta neighborhood. So that's why we need to needed to introduce that first. Okay, so let's introduce the definition of a function, the limit of a function of two variables. Let f be a function of two variables defined except possibly at the point x naught y naught and on an open disk centered at x naught y naught. So an open disk, this idea is a delta neighborhood, right? So we're looking at some sort of delta neighborhood centered around x naught y naught. Again, we plug values in that delta neighborhood into our function of two variables f, and we get our outputs. Okay, and we let L be any real number. Then the limit as xy approaches x naught y naught of f of x is equal to L. In other words, the limit exists and equals L if for each epsilon greater than 0, there corresponds a delta greater than 0, such that, this is supposed to, this is fine, such that if the absolute value of f of x minus L is less than epsilon, whenever 0 is less than the square root of x minus x naught squared plus y minus y naught squared is less than delta, right? So remember, what is this? This is the distance between the 2 points, right? And remember that the distance between two different points we think about being like the delta neighborhood, right? So what this is saying is that when I'm looking at a limit, if my point lies in a delta neighborhood, if my point xy lies in some delta neighborhood around x naught y naught, then the distance between whatever the limit is and my function value is very small, right? Epsilon, typically when we think of epsilon in mathematics, this is very small, right? Okay, so again, the idea when my x and y values are really close to that x naught y naught, then my z values or my output is really close to my limit, right? That's kind of the idea here. Okay, so and another big thing to point out too is in order to show a limit exists, it says if for each epsilon there corresponds a delta, right? So when we look at these proofs, what we need to do is find that delta. And then if we find that delta so that this happens, then we show that this happens and we're good to go. All right, so that's kind of the key, is to find that delta for each epsilon. So graphically, the definition of a limit of a function of two variable implies that for any point x naught y naught, or I'm sorry, any point xy that's not equal to that point that we're focused on, that x naught y naught, in the disk of radius delta, the value of f of x lies between L plus epsilon and L minus epsilon. So here's the idea. Maybe this will help kind of visualize a little bit. So remember, in the x and y plane down here, this is where our domain is, right? And so we have this nice, make it a little bit smaller, we have this nice, the disk right here. This is our delta neighborhood, our disk of radius delta. So if I pick a value that an x and y value, a point that lies in between there, then what I have to have happen is I have to have happen that, again, this is on, I should be able to draw this out like this and out like this, but remember this is in the 3 dimensions, so those blue lines kind of stick out a little bit weird because it's pulled out toward the page. So in other words, if I pick an input, an x and y value inside that disk, then my output needs to lie between L plus epsilon, right? L plus a little bit and L minus a little bit, right? Remember, L is right here in the middle and L is the limit, right? So the limit exists, whoops, make that a little bit bigger. The limit exists and equals to L if whenever I pick a value, an xy value that's really close or in the disk, here, let's do a different color. If I pick a value that's in the disk, when I pick that value and find its corresponding y value, it lies in here. If for every guy I pick, right, I pick this guy, it lies in here. If I pick this guy, it lies in here, right? If that happens for every single orange guy I pick, then I know that that limit exists and that limit is equal to L, right? So that's kind of the idea here of a limit in the 2 dimensions. So another way to phrase this, and it might be a little bit easier to phrase this when we start talking about proving it, is this limit exists if for each epsilon greater than 0, there exists a delta greater than 0 such that, and instead of saying that happens whenever that happens, we could say such that if 0 is less than the square root of x minus x naught squared plus y minus y naught squared is less than delta, then if whenever that happens, then we have that the outputs are less than epsilon. Okay, so in the case of a function of a single variable, in order to figure out if a limit exists, right, what did we do? We looked at the left-hand limit, we looked at the right-hand limit, and we said, hey, they're equal to each other, so the limit exists. Or for the example of like maybe like a rational function that looked like this and this, we said, okay, left-hand limit, negative infinity, right-hand limit, positive infinity, so it does not exist. Boom, done. Right? We just had to look at the 2 sides. Well, why did we just have to look at the 2 sides? Remember, the domain of those functions is just x values, right? It's one-dimensional. But now that we start looking at a function of more than one variable, we're looking at x and y values. So in other words, it's a point. And so when we look at a point in the x and y plane, we need to not just approach it from the left and right. It can't just be approached like this and this. It actually gets approached from every single value, right? And so again, in the case of a function of more variables, the statement x approaches x, xy approaches x naught, y naught means that we're approaching that point x naught, y naught from any direction, not just from the left and the right. It's from any direction. And that's why proving that a limit exists is the only way we can do that is by working with this big epsilon delta definition, because we have to take care of every single possible direction that it could come from. So again, if the value of this right here, this limit, is not the same when I approach from this direction or this direction or this direction or this direction, right? If it's not the same for every single direction, then the limit does not exist. All right, and that's the same idea as in the 2 dimension. If the left-hand limit did not equal the right-hand limit, then I knew that the 2-side limit did not exist. All right, same idea here, except it's from infinitely many directions. All right, so let's go ahead and look at example 1 here, since it's a relatively easy one. It says to find the limit as xy approaches the point 1, 2 from of the function f of the function 5x squared y over x squared plus y squared. So in this example, we can say that by properties of limits of products and sums, we have, well, I can look at the numerator. I can say that the limit as xy approaches 1, 2 of 5x squared y. Well, we know when we look at limits, we can just plug in the values if it's a polynomial. So when we look at just the numerator, it ends up being 5, 1 squared times 2, which is 10. And the denominator, we end up plugging in 1, 2 into x squared plus y squared, which equals 1 squared plus 2 squared, which equals to 5. None of those are 0, and more importantly, the denominator is not equal to 0. So we can just say, well, the limit of the numerator, remember for a rational function, when we take limits, the limit is equal to the ratio of the limits. In other words, I could take the limit of the top and the limit of the bottom if I didn't have any problems, right? If I didn't have a 0 in the denominator. So that still works here in the case of functions of more than one variable, right? So because the limit of a quotient is the quotient of the limits, and that's what I mean by you can just plug it at the top and bottom. And that, remember, that's true when the denominator limit does not equal to 0. We have that when I take the limit as x, y approaches the point 1, 2 of 5x squared y over x squared plus y squared is just equal to 10 over 5, the ratio of the limits, right? This is the numerator limit, this is the denominator limit. We can do the ratio of the limits and just find that that's equal to 2. Right? So in the case when the denominator is not equal to 0, it's just like in the case of functions of one variable when we looked at limits, it's just the ratio of their limits. Right? So how about this next example? If I just try to do the limit as x, y approaches 0, 0 of 5x squared y, that's going to be 0. So the numerator 5x squared y, that's going to be 0. And the limit as xy approaches 0, 0 of the denominator x squared plus y squared is also 0. So in this case, we can't just say, hey, it's 0 over 0 and does not exist, right? We can't actually, we can't make that jump the same way when I looked at, say, the rational function. If I looked at the limit as x approaches 0, we didn't just say, oh, it's 1 over 0, does not exist, right? Because even in the case, this one actually did not exist. But if I looked at the example of maybe 1 over x squared, I didn't just say, oh, 1 over x squared is 1 over 0 squared, which does not exist, boom, done, right? That wasn't right, because we know the limit as x approaches 0 of 1 over x squared is actually equal to positive infinity, right? So remember, in this case, we had to look at left and right hand limits and do a little bit more work. That's kind of the idea for example 2 here. We're not going to look at left and right limits, but we're going to do a little bit more work in order to figure out what this limit is. All right, so in the next video, we'll go ahead and pick up with example 2, and because I know you're all on the edge of your seat to figure out how we find this limit and what that limit is.